The goal of today's class is to help you understand how to predict the products of a chemical reaction. And so in order to do that, we'd be looking at a situation where we're given the starting material of a reaction, and you have to do two things. Number one, decide what type of reaction occurs, and then number two, after deciding what type of reaction occurs, number two, decide on the formulas of the reactants and products based on your knowledge of your formula writing skills. So this is a big step compared with identifying the type of reactions, trying to remember how to write formulas to predict the products. So if formula writing skills are weak, this is going to be a difficult step. So let me take you through that one bit at a time. So first of all, instead of trying to identify what type of reaction it occurs, let me screen this out for a moment. If we look at each of these reactions, and if we're told ahead of time that these reactions are synthesis, then we can look at the reactants, the starting materials here. In this case, the first one is potassium chloride, or excuse me, potassium and chlorine are going to react. If we know it's a synthesis reaction is one where you have two starting materials and they produce one product. So if you put potassium and chlorine together, if you go back to the beginning when we were doing chapter 7 and you look at the periodic table, hopefully you have a periodic table in front of you while you're doing this, you look at potassium, you find that it's in the first column of the periodic table. So it would have one valence electron. So when it forms ionic compounds, metal, non-metal, would be an ionic compound. The potassium would form a +1 ion. And then the chlorine, when it forms ions, it has 7 valence electrons. It's a halogen. So it would form a -1 ion. And so the formula of the product formed would be potassium chloride. After that, you could go about balancing it the way that we did balancing rules. What would you do first? You'd balance the metals. Potassiums are balanced. Chlorines, 2 chlorines here, 1 chlorine here. So what would be the first step? Would be to balance the chlorines by writing a 2 in the product side. Now the chlorines are balanced, but look, you've messed up the chlorines. So, the potassiums. So in order to balance the potassiums, you're going to have to come back, add a 2 in front of the potassiums. Now that equation is balanced. Try the next one. Try looking at the next one, the synthesis of the cesium and oxygen. You're going to have to go to find the cesium in the periodic table, figure out what charge ion it forms, knowing what charge ions oxygen forms. Think about the product of this reaction. If you're not finished predicting the products of this reaction, you might want to pause the podcast and think about it. How did you do? Right, cesium forms +1 ions. So when it combines with the oxygen, you'll form cesium oxide, CS2O. Now, is this equation balanced? No, it isn't. So again, you'll come through and balance the metal first. If we're using the MENO method, metals, ions, non-metals, oxygen, hydrogens, we have 2 cesiums here. We have 1 cesium on the reactant side. I'm going to come through and add 2 to the coefficient of 2 in front of the cesium on the reactant side. Now my oxygens aren't balanced. Oh, this is going to be a nightmare. You can see 2 oxygens here, 1 oxygen here, so I'm going to write a 2. Now I have a problem because now my cesiums aren't balanced. Now I have 4 cesiums. So I'm going to come along, change this, and now I have 4 cesiums produced, or reacted. Okay? Can you do the last one? This formula, I think whenever I write this, it kind of looks strange. Aluminum, what charge ions does it form? Do you remember? And what about nitrogen? What charge ions does it form? Ah, aluminum nitride is right. The aluminum forms +3 ions, the nitride -3 ions, thus we've correctly predicted the products. Now I'm going to leave this unbalanced. I'll let you try to balance yourself. Moving forward, if we have decomposition reactions, again, predicting the products is in the same fashion. If we have a reactant, if we have one reactant in a decomposition reaction, then we need to produce two products. In order to produce two products, you're going to have to look at the reactants and decide, okay, well, there's only two elements in the reactants. So, in that case, then the copper is going to be one of the two elements formed, and the oxygen is going to be the other element formed. Before you say you're finished, you have to think about, okay, now, what are either of these two products do you need to write them as diatomics? Oh yeah, I remember now. The copper is not diatomic, but the oxygen is. Going forward, if you wanted to say, okay, what are the states of matter? Well, copper oxide is an ionic compound, and all ionic compounds are solids. So we could put the state of matter for the copper oxide there. We could also put the state of matter for the copper metal, because I know copper metal is a solid, and I also know that oxygen is a gas. So in decomposition of a compound that only has two elements, it's pretty easy. You're going to break it down into the two elements that are formed. So again, another example, when you decompose nitrogen, you're going to be forming nitrogen, again, a diatomic. It's a gas at room temperature. And hydrogen. Also diatomic, also a gas at room temperature. Now, the next one looks kind of tricky, but actually I'm giving it to you because it should look familiar. Remember your hydrate lab? It was entitled Decomposition of a Hydrate. With a hydrate, you have two compounds that are stuck together. Remember how we talked about stuck like glue? Okay, well, these two hydrates, let's look at the first one, magnesium sulfate, heptahydrate. Magnesium sulfate heptahydrate is two compounds stuck together. One of the compounds is magnesium sulfate, so when I decompose that compound, you'll get two products, the magnesium sulfate, and the second product is water. What state of matter was the magnesium sulfate? It was a solid. And what state of matter is the water? Well, you saw it. Really, you didn't see water liquid being formed because you heated it up. Oh, we could put a little delta sign here to show you that you heated up the starting material in order to produce the products. The product that you formed for the water was in the gaseous state. And is this equation balanced? No, we would have to put a big 7 in front of the water to say that when magnesium sulfate, heptahydrate decomposes, you form 1 magnesium sulfate and 7 waters. Let's take this reaction down here to give me more space. Copper sulfate, pentahydrate, that was the blue colored crystals, whereas magnesium was the white crystals. If you remember, I'm not sure. You might go back to that lab in reviewing for your exam as well. Go back to that lab, see which hydrate you have. Look at the terms that we used in those labs. Very valuable lesson at this stage of the game is to be reviewing what you learned in lab this year, especially with new eyes now that we're in formula writing. You should be able to see a whole lot more now looking backwards. So you took these blue colored crystals, if that was your hydrate, you decompose them, you'll again produce what we call the anhydrous salt. It was a solid, and we produced water. The water was lost. We calculated the percent water lost. This was when we were first learning moles. We found the moles of copper sulfate. We found the moles of water in that lab. And then you compared the mole ratio of water to the mole ratio of copper sulfate. Look back at this lab. And if you did this experiment and you calculated the mole ratio of water to copper sulfate, I'm fairly certain that the mole ratio that you found in that lab was 5 waters. You didn't know it at the time, but we were doing a balanced equation. All right, now moving forward to the next type of reaction, combustion. When we burn a hydrocarbon, if we have what's called complete combustion, with complete combustion, then the same products are produced in every case when you burn a hydrocarbon, CO2 and water. They'll be in the gaseous state because all complete combustions produce a lot of heat. So I could even write the word heat on the product side. I'm not going to do that now. That would be a sign of an exothermic reaction when heat is produced. But in this case, water and CO2 is produced. In the case of burning gasoline, when you burn gasoline with oxygen, notice oxygen is a reactant in every case with combustion. In this case, with a hydrocarbon, a compound that contains carbons and hydrogens, you get the same products again, CO2 and water. Finally, ethanol. Some of the gasoline alternatives use ethanol. Ethanol combustion, again, same products, CO2 and water. The only difference in all of these is the challenge of balancing those. And I'm not going to leave those to balance now. You can do that on your own. 2 more. Double displacement and single displacement. With double displacement reaction, the best way to look at this is that you are going to have a reaction where you have 2 compounds. They're generally considered ionic compounds, or in this case an acid, where you have a positive ion and a negative ion in one compound, and a positive ion and a negative ion in another compound, and they're going to trade partners. So in this case, the hydrogen is going to get together with the hydroxide on the product side, and the sodium is going to get together with the chlorine. So when I write the products of this reaction, combining the sodium, which is +1, with the chlorine, that is -1, I can write the formula sodium chloride, NaCl. Likewise, hydrogen and hydroxide, I always put the positive first. So I have the second product is water. Now it looks like I don't have much time left for this podcast, so what I'm going to ask you to do is to finish the rest of these for homework and bring those in to class tomorrow, because I just want to show you quickly an example of a single displacement reaction, and then I'll ask you to finish the rest of those. With single displacement reactions, remember, you have a metal displacing hydrogen out of water. You can have a metal displacing hydrogen out of an acid.